My dear student, colleagues, and all the viewers who are watching this program live from Facebook page, Physics Center, and YouTube channel. So I'd like to welcome you all to our international physics webinar. Good afternoon to all. I think you have already come to know that the Department of Physics, Pabna University of Science and Technology, has started its online program, including online international physics webinar. So, and we have successfully completed our 211th International Physics Webinar, including 3 Nobel laureate speakers. So, we are trying to adjust with this new normal situation, as you have already come to know that it is very difficult for us to continue our normal academic program inside the campus due to the COVID-19. So, we have to start our online program. So today we'd like to welcome you all to a joint session between our department, Department of Physics, Pabna University of Science and Technology, and the Department of Physics, IIT Kanpur, UP, India. And we have with us here today Dr. Satyajit Banerjee, sir, Professor, Department of Physics, IIT Kanpur, India, and he has already connected with us. So I'd like to welcome our speaker. Sir, namaskar. Good afternoon, and thanks for accepting our invitation, and thanks for giving us
I'm
this
very happy.
opportunity. Yeah, to arrange such an important webinar, sir. So before going to you, sir, I'd like to introduce you with our student and viewers. So dear student and viewers, I think you have already come to know that the title of this today's International Physics Webinar, and this is very exciting webinar, and title is also very exciting, Introduction to Superconductivity and some modern areas and application. And our speaker is Dr. Satyajit Banerjee, sir, Professor, Department of Physics, IIT Kanpur. So you can see his academic and career background. Dr. Satyajit Banerjee sir is currently working as a professor at the Department of Physics at Indian Institute of Technology, Kanpur. And we can see he has completed his PhD in 2000 from the Tata Institute of Fundamental Research, TIFR, Mumbai, India. And he joined IIT Kanpur in 2004 as an assistant professor, and before that he was a postdoctoral researcher in the Weizmann Institute of Science, Israel, and he stayed there up to 2004. His research area is superconductivity, magnetism, and exploring these phenomena in 2D materials and their heterostructure and nanostructure. So thanks, sir, for joining with us, and thanks again for giving us this opportunity. I think our student will learn a lot of things about superconductivity by this webinar, sir. It's your time, sir. You can start your session, sir.
Okay, thank you. Thank you, Pritam. Thank you for the nice
It's my pleasure,
introduction.
sir.
And I'm very happy to be associated with this webinar, international webinar. It would have been very nice if I could have visited your country, your beautiful
Yeah,
country,
of
and
course,
come
sir.
there.
I'll definitely invite.
And I would definitely look forward and even would like to invite you to come to India at some point of time.
Sir.
Once things improve, and I hope all of you all are safe and stay safe. With that, I would sort of like to begin with this topic of superconductivity. And this topic of superconductivity is a very vast topic. It has many, many aspects to it. And let me start the pointer. It has many aspects to it. So I will try and touch upon those aspects in the simplest way possible without getting into any details and complicated, expressions and formulations. I will try to give you it from a practical point of view and then lead on to the essential aspects. So it will be a broad overview in that sense, and try to show you what are the modern areas and modern developments which are happening in this. I'll give you some brief pointers to it. So with that, let me sort of begin. I am from the Department of Physics at IIT Kanpur. I invite you all to visit our department, our institute at some point in the future. And so let's start. The topic of superconductivity, as I said, is very vast. Started it around beginning of 1900s, and it started with actually Kamerlingh Onnes, and he actually got the first Nobel Prize in 1913. And since then, there have been at least 5 Nobel Prizes which have gone to this phenomena of superconductivity alone. and to different aspects of superconductivity. So these are, Guyver and Josephson in 1973, Bardeen and Cooper and Schrieffer for BCS theory in 72, George Mueller, Bednorz and Mueller in 1987 for discovery of high temperature superconductivity, and Abrikosov and Ginsburg for discovering the mixed state of type 2 superconductors. So I will try and touch upon these points in the talk in whatever way it is possible, and how things are moving ahead in these different directions. So I will start it off with a historical perspective, trying to give a brief history, and then through applications I will try to introduce some of these aspects to you as I go along. So the plan is to give a brief history of how superconductivity was discovered, then go on to some of the topics which are important, which is essential for understanding superconductivity. So I will talk about the Meissner effect. I'll talk about the Vortex state in type 2 superconductors. And when I talk about these things, I will give you applications also simultaneously. I'll give you a very hand-waving argument of BCS theory, how you can understand the BCS theory in a very quick and a very general way, but in a very hand-waving fashion. And then come to Josephson phenomena, a very, very important aspect. A Nobel Prize also was given to this. And then as I go along, there will be applications all across when I discuss all of these topics. So let's begin right from the beginning. So you know that materials, various liquids have different boiling temperatures. Water boils at 370, 300 degrees centigrade. If you keep on lowering the temperature, then mercury freezes at 234.4 degree Kelvin. Okay, this is all in Kelvin, which I've shown here. Water boils at 100 degrees centigrade, which is 373 degree Kelvin. Okay, and you can keep on reducing the temperature, and then different gases start freezing out. Carbon dioxide freezes out at around 195 Kelvin. Oxygen becomes liquid at 90 Kelvin, so it actually boils, and the oxygen, the gas liquid temperature is, the gas to liquid transition temperature is 90 Kelvin. Liquid nitrogen is 77 Kelvin. Okay. And then if you keep on cooling further, you go to helium. Liquid helium is at 4.2 Kelvin. Okay. It is actually very difficult to actually liquefy helium, because helium atoms are very light. After hydrogen, you have helium. And so if you want to liquefy anything, you have to bring the atoms close together, and light elements, light atoms can actually move around a lot, so it becomes very difficult to make them lose their energy. Helium is also inert, so the interaction between the atoms is very weak, so it is very difficult to liquefy these atoms or liquefy helium. And Camerlingh-Onnes was the first one who actually very successfully was able to liquefy helium. It took him, of course, 11 years to actually liquefy helium. And basically what he did was he used the Joule-Thomson effect, which you have studied, that when you do a free expansion of the adiabatic expansion of a gas from high pressure to low pressure region, there is a cooling of the gas. And basically he used that in a regenerative method to actually liquefy helium. He was the first one to succeed in liquefying helium. And he was able to reach a low temperature. Helium liquefies at around 4.2 Kelvin. So he was able to go down to 4.2 Kelvin, just a few Kelvin away from absolute zero. This is his system that he had developed for liquefying helium in Camerlingh-Onnes' lab in Netherlands. And this is Camerlingh-Onnes. This is the setup which looks in color picture, which is still there in University of Leiden in Netherlands. The technology has changed since then, and now it is a very modern technology. This is a cryogenic plant which produces liquid helium, and this is the modern version of it, which is slightly different. I mean, quite different from what you see here, all these pipes and everything. But essential principle of the Joule-Thomson effect remains the same. But why were people interested to actually liquefy helium? Okay. So at the point when early 1900, around 1900, people were actually wondering, or even in the 1800s, end of 1800s, people were wondering that platinum, the resistance of a metal, as you reduce the temperature, of course, it goes down, it keeps on going down. But then what happens when you, just one second. Let me move this to the side. Okay, it's not able to. One second. So platinum actually reduces temperature and its resistance goes down. But how does the resistance of platinum actually reduce when you go down to zero temperature or very low temperatures? In the late 1800s, people only were able to reach about 14 Kelvin. So up to 14 Kelvin, the resistance continued to decrease. But as you reduce the temperature further, the question was that does it actually go monotonically to zero, or does it remain flat, or does it increase? And there were various theories which actually said, Lord Kelvin said that no, below a certain temperature, the resistance should increase. Some people said that no, it should monotonically go to zero, and some people said it should be a mean of the two, so it should remain flat. So the only way to actually confirm this was to actually reduce the temperature, and that is why Kamerlingh Onnes was working very hard to actually reduce the temperature down to 4.2 Kelvin. He did reach 4.2 Kelvin, and what platinum showed was that it became flat. Okay, the resistance of platinum actually saturates out, and that is because of impurities in platinum. So now he wanted to actually see what happens if you take a metal which is very pure. And very pure metal you can actually obtain by mercury, because mercury being a liquid, you can make it undergo distillation. You know that if you take water and you distill it, it will get very pure water. Mercury is also a liquid metal. You can make it undergo distillation process and you can make it very, very pure. So he took pure mercury. And okay, before I go to the story of mercury, modern cryogenics, I told you, reaches 4.2 Kelvin, but that is with helium-4, which is the actual isotope of helium. But if you use helium-3, helium-4 mixture, and you can do something called as a dilution refrigerator, then you can actually go down to 10 millikelvin. Okay. And then with adiabatic demagnetization, which is, you may have studied about it, with high magnetic fields, you take a paramagnetic salt, magnetize it, and then demagnetize it. You can reduce the temperature. So if you use this adiabatic demagnetization, you can go down to 50 millikelvin. So people in cryogenics now can reach down to 50 millikelvin temperature, and you can really explore physics at just a few millikelvin from zero, absolute zero. So all that is now possible in labs. At Tata Institute of Fundamental Research, there is a lab which actually does microkelvin experiments. So from 4.2 Kelvin, you can see that it is a log scale. You can go down to about microkelvin ranges. Okay, so that is where modern cryogenics has reached as a current state of the art. Okay, so what Kamerlingh Onnes was that, okay, now if you take a pure mercury, you make mercury very pure, what happens to mercury's resistance if you start cooling it down? So he took a U-tube, a glass U-tube, in which he put mercury, and there are these two arms of this mercury. The two ends of this mercury are actually connected to a Wheatstone's bridge, which you would have studied, so that you can measure the resistance of mercury. And he started cooling down the temperature with his liquid helium. And when he cooled down this mercury, then abruptly at 4.2 Kelvin, there was a huge drop in resistance. The drop in resistance was orders of magnitude. You can see here that the resistance of mercury is about 0.1 ohms, and then at about 4.2 Kelvin, the resistance goes below -5 ohms. So it is few orders of magnitude drop in resistance. And this was the first time the superconducting state was discovered. Namely, that it is a material, if it is cooled below a certain temperature called the critical transition temperature, then the material becomes, resistance of the material tends towards zero. Okay. So if you take a material and you measure its resistance, then below its critical transition temperature, the resistance of the material becomes immeasurably small. It becomes very low. So the Wheatstone's bridge method, which Camerlingons was using in 1911, this was the discovery which happened in 1911. This is his notebook in which he said, here it is mentioned that resistance actually becomes zero, where the resistance goes below whatever was the sensitivity of his instrument was -5 ohms. So it is below -5 ohms. So this is the transition of a material into zero resistance state, or what looks like a zero resistance state. It becomes immeasurably low. So this was the birth of superconductivity, a fantastic phenomena in which suddenly the material loses all resistance. And you know that resistance comes because electrons are flowing inside the metal and they are colliding, they are hitting atoms or undergoing collisions, and that gives rise to resistance. So below the superconducting transition, suddenly the metal loses all its resistance. Okay, there is no resistance which is experienced by these electrons, and they can just flow without any resistance. So this was the birth of superconductivity, and this was the first Nobel Prize which went to Camerlingons, not for liquefying helium, but that discovery was very important because it gave birth to superconductivity phenomena. Okay, he was able to actually find superconductivity in mercury for the first time. So let's go on with the story. And the story goes that how do you actually measure what is the lowest resistance that the superconductor can actually go to? Is there a way? You cannot use this simple method of measuring resistance. So what people did, and actually this was also tried by Camerlingons and other people have also tried it in different ways. This is an interesting experiment, is that if you take a coil of a superconducting wire, lead, Camerlingons took a lead wire, you take a loop of lead wire and set up a current in this lead wire, and if you cool it, then because the resistance becomes zero, the current which is circulating in the wire will continuously circulate. Okay, so it will never decay out, and this is the phenomena of persistent current, that if you take a loop of wire and set up a current in it, and if the material becomes superconducting, namely its resistance becomes very very low, then the current will circulate without dying out, because resistance will cause the current to die out inside any material. But if the resistance becomes immeasurably low, then the current will circulate. So the time for which this current that you have set up circulates is actually depends on the resistance of the material. So what they did was that they took this loop of current and they dipped it in liquid helium, and then they studied how long does the current decay, how long does it take for the current to decay, because based on that you can find out the resistance. And experiments have shown that the resistance, the decay is extremely weak. People have run this experiment for hours together and the current does not decay. The current continues to flow. So if you apply a current and switch off your power supply, you can put in current into a loop of wire and then remove your power supply. You can set the current up and it will it will continuously circulate in this for indefinite period of time, and based on these experiments they have obtained upper bounds on the resistance, that the resistance in the superconducting state should be less than 10 raised to minus 19, almost zero for all practical purposes. So persistence of current is a very important and a very interesting outcome of superconductivity, because the material goes into the zero resistance state. So you can take a wire, for example, and if it is superconducting, because R is equal to 0, you don't need any power, you don't need any voltage to actually send in current. You can apply the current in the wire. If it is superconducting, you can remove the power supply and the current will still go on inside that wire. Okay. So this is a very fantastic sort of, and it has many applications, possible applications. I'll come to that very soon. That's why I wanted to introduce this concept of persistent current, which can come about in superconductivity. Now, is superconductivity a rare phenomenon? This is the periodic table, and whatever is colored in the periodic table are the elements which are superconducting. So you can see that various elements in the periodic table are all superconducting. Some of them you need to apply pressure to the material to make it superconducting. Otherwise, in their native state, they are not superconducting. So, but certainly you can see that superconductivity, whatever has been discovered till now, these are all superconducting. Okay, all of these colored areas, whatever are these colored blocks, are superconducting materials. Okay, and so you can clearly see that it is not a very rare phenomenon. And from 1900 onwards, mercury was discovered in 1911. Then superconductivity in lead was discovered, and people kept on discovering, of course, not only elements, but there were alloys and different combinations of materials got discovered, and the superconducting transition temperature kept on increasing. Okay. By the 1980s, for example, niobium 3 Ge, okay, the superconducting transition was around 20 Kelvin or so. Okay. But then in 1990s, there was a sudden huge leap in the superconducting transition. A new class of materials were discovered called high Tc superconductors, which actually shot the superconducting transition temperature, the temperature at which the material loses resistance. That transition temperature, which was hovering around 20 Kelvin, suddenly jumped up to around 150 Kelvin. Variety of these copper oxide based materials were found, and all of these materials actually showed very high superconducting transition temperatures. This was very important because now you can have materials which you can use. They are of course not room temperature, but they are close to room temperature. So you may use them for applications of superconducting wires and so on, which you can use for applications at room temperature. So the discovery of high Tc superconductivity was a major breakthrough, and this was where another Nobel Prize was given to Bednorz and Muller for the discovery of high temperature superconductivity in this YbCO material. It's called yttrium barium copper oxide. But after that, a whole lot of other high Tc materials, which are these copper oxide based systems, these are called as ceramic materials. They have been discovered. Okay, so this was the story as far as high Tc was concerned. The story continues further, and in 2008 a new class of materials were found, which are called these iron arsenide materials, which are a different class of materials compared to these copper oxide high Tc materials. Another new class of materials were discovered whose Tc was not, of course, as high as high Tcs, but they came in the range of between 50 to 100. But they were not copper oxide based, they were iron and arsenic based. So this gave rise to another new area of superconductivity called iron arsenide superconductors. So that happened here in this range. Okay, and currently a lot of research is going on into trying to understand this other class of superconductors, which are called as iron arsenide class of superconductors. Very interesting physics is associated with them. So people are still trying to understand how does superconductivity appear in high Tcs, how does superconductivity appear in iron arsenides, and these are two major blocks of understanding which are going on. This is the traditional, very mature area of physics. This is a new area and it's a developing, emerging area, but still from 2008. So it's relatively new compared to high Tcs, but there is a lot of work going on here also. Along with that, there are various new superconducting materials which are being discovered. 2D quantum materials, topological insulating superconductors. I will have a little bit to say about 2D materials and superconductivity in them. Interfaces. You can take interfaces of two different materials which are non-superconducting, and at the interface you find that superconductivity appears. So there is interfacial superconductivity and various interesting new phenomena which of late in the last few years has been discovered. And one of the most exciting new discoveries has been superconductivity very close to room temperature, almost 300 Kelvin. And that is in a material which you wouldn't even have guessed. That is in high temperature. This is in hydrogen sulfide, carbonaceous hydrogen sulfide, a mixture of hydrogen sulfide and methane at very high pressures, of course, of around 267 gigapascals. So just to give you an idea, if 1 atmosphere is the atmosphere around us, is the atmospheric pressure around us, 267 gigapascals is like 26 lakh atmospheres. Okay, so these are very, very high pressure experiments. But in high pressures, this gas and this carbonaceous mixture actually liquefies, solidifies, and then actually becomes superconducting. And the amazing thing about this superconductivity is that it is shown to be nearing room temperature. So this scale was at 200 and no one ever had reached beyond 150, 180. But these high temperature, high TC materials or these hydrogen sulfide hydrides have actually crossed the barrier. So this is in 2019, this discovery happened, 2018, 2019. So this is the latest current development, and people are very excited that maybe we might reach in some few more years a possibility to have high temperature superconductors which operate at room temperatures. So that is a certain definite possibility. So this is as far as state of the art of materials are concerned and how much TCs that they show. So now let us look at a little bit of application. So superconductors can be used for power transmission. Okay, the potential is for power transmission. This is an ordinary cable which you use for power transmission. It has these copper wires, cores, and they have multiple cores inside it to carry wire, but these always have resistance inside them. So to send in current through them, you will have to overcome the resistive losses because these get hot because of resistance. So you have to supply power so that you can actually send the current and reach it to your homes. Okay, so there is power loss. It costs a lot of power. There are distribution losses and so on because of heating and so on. So people are thinking, how about using superconducting wires? And this is the latest set of wire. It's a complicated wire, not as simple as your current wires which are currently available. But this is the latest industrial wire which is using a superconducting wire through which you actually circulate liquid nitrogen. It has high temperature superconductor inside it. Okay, and it has a high temperature wire. Instead of using a copper wire, you use a high temperature superconductor, okay, wires out of it, and then you have to circulate cryogens inside it so that you can cool the wire, because these wires are still not at room temperature, but they can be cooled with liquid nitrogen so that they are below the superconducting transition. YBCO has a superconducting transition of 90 Kelvin, and BISCO has a superconducting transition also around 100. Certain phases has above 100, so 100 Kelvin. So with liquid nitrogen, which has a boiling point of 77 Kelvin, if you circulate liquid nitrogen, you can cool these wires. So these sort of wires are being developed that can they help in transmission, zero loss transmission of power. Of course, you will have to circulate cryogens and so on. So there are these aspects which come into the picture. But these are the futuristic technologies which are developing using superconductors. Another very important area of development is in developing magnets. Okay, and in magnet development, you will have a copper sort of a matrix, and inside this copper matrix, these shaded regions that you see are superconducting wires. Okay, so these are NBTI wires, and these have been used for winding huge magnets. So the MRI magnets which doctors use, in hospitals for actually checking your brain, your spine, or any other issues, you would have seen an MRI machine inside a hospital. These MRI machines, whatever you see here, is actually a superconducting magnet. There is liquid helium inside it, and there are wires which are made of this NBTI. Okay, they have a copper matrix in which this blue color is the NBTI wire. Okay, and this is superconducting, and you have to cool it with liquid helium. So there is liquid helium inside it. There are these rolls of, it's a solenoid. Okay, and what you do is that it is a coil of wire. You apply a current and then you stop the power supply. The material is superconducting, so the current keeps on circulating inside the solenoid as long as it is cold, and it will generate a magnetic field. You know that any solenoid, if you pass a current through a solenoid, V is equal to nu 0 n into I. Okay, that will generate a magnetic field inside the solenoid. So inside the solenoid, the magnetic field is generated here in this bore where the patient is put in. There is a magnetic field of up to 9 Tesla which can be generated, and no power supply is used, because initially you charge the coil with the current. It's a loop of wire, it loops of wire, many turns are there, but then once it is superconducting, the current will remain in it for permanently as long as you maintain the superconductor cold. So you can remove the power supply, you put in a lot of current, but that current keeps on circulating, and that's the advantage of superconductors, that you can maintain persistent current. So huge amount of applications are there, and one day-to-day life application is used in MRI magnets, which every hospital everywhere uses, and these are all superconducting magnets. Inside it, they are made with these NBTI superconducting wires, the solenoids which generate these magnetic fields, and they don't need any continuous power supply, so they are energy efficient. You just have to continuously fill in the liquid helium inside this region. So these are very important applications which have come up with superconductivity, and even newer applications are being developed. For example, windmill technology, energy storage devices which are using superconductivity. I don't have the time to get into the details of them, but they are almost along all these lines. So in terms of energy efficiency, it is a very lucrative and very important area of work. Now let me tell you a very interesting effect, which is the Meissner effect. Okay, so if you take a loop of wire, and if you know the Lenz's law. Okay, you know, if you have a metallic wire and if you change the magnetic field, then the rate of change of magnetic field will induce a current. Okay, it will try to oppose the change in magnetic flux. So what will happen is that current will circulate inside it opposite to the direction of the magnetic field, and this changing magnetic field will be opposed. So it will try to oppose the change in magnetic flux. So if you try to move the magnet inside this loop, currents will be set up and they will generate a magnetic field which will try to oppose this change. Okay, so this is basically the Lenz's law, but the Lenz's law in a normal metal works for changing magnetic flux. Only if your magnetic field is a changing magnetic field, then the material actually responds, or the metal actually responds by setting up its own currents, which are called as shielding currents, to prevent the change in magnetic flux. So the Lenz's law works to generate shielding currents only if you have a changing magnetic field. But the Meissner effect, the superconductor, has a very important feature, namely that if you take a material and irrespective of how you have cooled it, whether in a magnetic field or without magnetic field, you cool it, and if you apply a magnetic field, it will always expel all magnetic field from within its interior. So if you apply magnetic field, the magnetic field cannot penetrate into the superconductor. They will actually avoid the superconductor. So what the superconductor does is that it sets up currents inside it, shielding currents, almost like the Lenz's law. But these are very large shielding currents which actually prevent any magnetic field from entering into it. So if you have applied a magnetic field, current will start circulating in a way that it applies a magnetic field to cancel the applied magnetic field. So the net magnetic field inside the sample becomes zero and the field actually does not enter. So This happens irrespective of whether it is a changing magnetic field or a constant magnetic field. Okay, the important feature of Meissner effect is that whether it is a changing magnetic field or a constant magnetic field, a superconductor will always expel magnetic field from its interior. And this property is known as diamagnetism. You might have studied in your books about, when you have studied about magnetism, namely diamagnetism, namely the ability of a material to expel magnetic field from within its interior. Most metals have very, very weak diamagnetism. The diamagnetic susceptibility is like 10 raised to minus 6 in normal metals. A superconductor on the same scale has a susceptibility of diamagnetic susceptibility of -1. So normal metals have -6 diamagnetic susceptibility, 10 raised to -6 diamagnetic susceptibility, and the superconductor has few orders, 10 raised to 6 orders of magnitude higher diamagnetic susceptibility. So very strong diamagnet. And what is the thing about this diamagnet? So if you take a superconductor and if you bring a magnet close to it, if this is the north pole and this is the magnetic field, a superconductor, inside a superconductor, because of the strong diamagnetic susceptibility, it will set up shielding currents which will circulate in a direction so as to oppose this magnetic field. So if this is north pole, because of the circulating current, this is also like a north pole. So it behaves like as if your diamagnet, it is actually behaving like a magnet which is trying to repel this magnet. So this magnet, so north pole faces will repel each other, so you cannot bring the magnet any further close. And in fact, if you do it correctly, then this magnet, because of the force of repulsion between the superconductor and the magnet, this magnet can also start floating. Okay. So a superconductor has extremely strong diamagnetism compared to a normal metal. Okay. Its ability to throw out or expel magnetic field by setting up shielding currents inside it is extremely strong, and that leads to this Meissner effect, because if you apply a magnetic field, it will set up shielding current so as to oppose the magnetic field, so that inside the superconductor there is no magnetic field. And this is the common property of a superconductor. And this diamagnetic property of the superconductor has important applications also. And so let me show you a small demonstration here. So for that I need to stop the pointer. So here what you see here is a superconductor, and here you have a magnet. This silver colored thing is a magnet. So a person picks up the magnet and places it on top of the superconductor, and you can see that the magnet starts floating. Okay. It is because the diamagnet, this material is a superconductor. It's actually a high temperature superconductor which has been placed in liquid helium. Okay. So the floating happens because of the Meissner effect. It is like two north poles which are repelling each other. Okay, let me show you. So if you want to see it again, I think I will have to run it again. So just for you to see it again, here this north pole comes here, and there is another north pole which is generated because of diamagnetism, and now these two are floating. So this you can create levitation in superconductors. But what is interesting is that it is not an unstable equilibrium. You can see that if I run this, it's slightly more complicated to understand, but again, very interesting experiment is that you cool the superconductor. The person poured actually liquid nitrogen to cool the superconductor. You can see floating, but now you can also, when you pick it up, you can see that there is no connection between the two, but the magnet actually lifts up the superconductor. So not only there is diamagnetism, there is some bit of attractive component also. Okay. And that is coming because of another effect called vortices, which I will tell you a little bit later. So the Meissner effect is not the only thing, namely diamagnetic response is not the only thing. There are other features are also going on inside the superconductor. However, this levitation which I showed you, namely the magnet floating on top of the superconductor, you can use it for floating trains. Okay, and then the trains can float on tracks. Inside you have superconductor, on the tracks you have a magnet, and your train can actually be floating on top of the track, and then they can move at very fast speeds. Okay, there is no friction. Okay, so Japan and so on have been trying to develop this type of a train which can go at extremely high speeds, and there are prototypes developed, but there are cost issues and so on. But these are futuristic technologies. Hopefully we will get to a stage when these can be actually realized in day-to-day life. So there are these amazing technologies which are being developed, which are based on this phenomenon of levitation. Okay, so let us continue further. Okay, and this experiment where it was lifted was because little bit of flux lines actually can enter into certain class of superconductors, and they actually bind the magnet with the superconductor. So apart from repulsive forces, there is weak attractive forces which are generated because of these lines which are entering into the superconductor. These are called as vortices, and they actually lead to the system getting attracted. Not only repulsion is there for levitation, but also some bit of attraction is there, and that is why it's not an unstable equilibrium. Any repulsive force will give rise to unstable equilibrium. You need attractive forces to make it like a stable equilibrium. Okay, and that stable equilibrium is generated by these. So I'll come to these very quickly very soon. So this was the Meissner effect. So now I have about, how much time do I have, Pritam?
Yeah, about 20 minutes.
20 minutes. Okay, so I'll try and go very quickly. So now let me change the story slightly, and let's go on to something called as a Large Hadron Collider. Pritam is actually also a high energy physicist, I think. So these are experiments where you take protons and you take them at very high energies and collide them. Okay, and in the process they generate a lot of particles, and you can actually look what is what goes into building up a proton, what are there inside these fundamental particles. So a lot of very interesting experiments go on, but for these experiments you need to actually move protons at very high speeds, and they actually, there are two counter propagating beams of proton which go and strike. So they turn and then they go and strike. Okay, and so these are very high energy experiments. So this is at the Large Hadron Collider at CERN, where protons are accelerated to 7 TeV, and 1 TeV is around 10 raised to 12 electron volts. So these are very high energies, and this is actually done at CERN. Below the France-Swiss border, there is this 27-kilometer line in which you can see this weak circle which I have shown here. Okay, let me use a pointer. Here you can see this is the circle, okay, where these protons are accelerated. So there are two counter propagating beams of protons which travel in a circular trajectory, and they will go and strike at some point, and then there are detectors. Okay, so this is on the French-Swiss border near Geneva. There is this experiment which happens. It's a multi-country experiment. So this is the circle in which the protons which are accelerated to very high energies, they actually are made to turn in this circle, and then they go at strike. There is one beam which is traveling in one direction, there is another beam which is traveling in the other direction, and then they go and strike. So now if you have beams of protons, protons are charged particles, how do you make them go in a circle? Okay, so if these are so high energy beams, the only way to make them or steer them so that they are actually moving in a circular path is to use magnetic fields. With magnetic fields, F is equal to Q into V cross B. You know this law. This will actually allow, so with the use of a magnetic field, you can actually force the protons to actually turn inside this circular path. So magnetic fields are used. Okay, and if you are moving, your beams of protons are moving at very close to the speed of light, 99. They have been accelerated so much at such high energies. If you need to steer these beams so that they continuously turn and accelerate and then move in a circular path, then you need to actually apply very strong magnetic fields. So how are these strong magnetic fields used? So there are these, this is the tube, okay, this is the tube in which the protons actually accelerate, okay, this is the part of the tube in CERN, okay, and this tube that is shown here, this circle, this is a section of that tube, and in that section there are these superconducting magnets, okay, and these superconducting magnets generate about 10 Tesla of magnetic field, okay. You have superconducting wires, and so around this 27 kilometers, you actually 60 tons of liquid helium is circulated, so that you can actually cool these magnets to liquid helium temperatures and then generate such high magnetic fields. And there are 1234 such magnets all along this length of the circle, okay, and these are all superconducting magnets. Now so this is where your applications also come in for fundamental physics. So not only in condensed matter physics or solid state physics, superconductivity finds its application in high energy physics, in setting up experiments for high energy physics, medical physics, a whole lot of other areas where it is revolutionizing things. So let me tell you about a problem which happened in 2008 when the LHC was commissioned, that the region where the liquid helium was around the magnet has these wires, superconducting wires. Suddenly it was found that the wires got very hot and the liquid helium boiled out, and it completely damaged the section of the line. Okay, you can see the damaged portion. The line got completely damaged because the liquid helium boiled off and it became like a gas, and inside a container, if the gas volume suddenly increases, the pressure will rise and it will completely damage the container. So the region where the liquid helium was, suddenly that container got damaged and the liquid helium escaped from that region because the superconducting wires suddenly became very hot. And what was the reason for the superconducting wires to get hot? Because you know that once the superconductor is below its transition temperature, its resistance should be zero. So there is no heat generated. I square R is zero. So whatever be the value of current, the power dissipated in the superconductor is always zero. But how did the superconductor get hot? That heating happens because there are certain class of superconductors. I told you that a superconductor is a Meissner state, namely it will all expel magnetic flux from within its interior. That is for certain class of materials called type 1 superconductors. But there is a very large class of superconductors called type 2 superconductors, in which actually the superconductor breaks up into normal and superconducting regions, in which there are these small whirlpools of current which are created. So the superconductor, of course, is fully Meissner-like, but in certain pockets, in certain regions, there are these small whirlpools of current which are created. Okay, small normal regions are created, and these whirlpools are called vortices. They are normal regions, so certain pockets. This happens only when a superconductor is placed in a magnetic field. So a type 2 superconductor, if you place it in a magnetic field, a strong enough magnetic field, then the superconductor breaks up into superconducting and normal regions, where microscopic regions inside the superconductor actually turn normal. And you can see that whether certain elements are of type 1, but there are whole other lot of materials which are used for applications are all type 2 superconductors. Namely, in a magnetic field, there are these small normal regions which are generated, which actually become normal. Okay, and they carry a magnetic field. Okay, and this is the picture that I show you, that when you take a superconductor and apply a magnetic field, then inside these microscopic regions, the superconductor actually is lost. It is a normal metal here, normal material here. Outside it is still superconducting. And these are called as vortices. These are those small whirlpools which I showed you here. So this is a very exotic phenomena where you will create these small whirlpools. You know, these are like, you know, that you take water and you circulate it and you will see the swirling of water inside it. These are also the same thing, but instead of water, these are actually currents. These are actually electrons which are swirling around. So these are normal regions around which electrons are swirling around, currents are swirling around, and there is a magnetic field inside it. There is no magnetic field in between vortices. Namely, in the white regions, there is no magnetic field, but inside these regions, inside these vortices, there is a small magnetic field which is present. So the superconductor beyond a certain value of magnetic field actually breaks up into normal and superconducting regions. It's no longer a fully superconducting region, but there are portions which are these where it becomes normal. So it is like a tube where around this tube, each of this vortex around this tube, there are currents which are circulating, and inside it there is a very small magnetic field which is present. If I measure the magnetic flux in this region, the magnetic flux is which is field into area. If I integrate the magnetic field over this entire area, it is 2 into 10 raised to minus 15 Tesla meter square. So each of this is actually carrying some small magnetic field, and they have a whirlpool of current which is circulating around it. And these are microscopic objects because the diameter of each vortex is around 10 nanometers. So 1 nanometer is 10 raised to minus 9 meters. So you have these small whirlpools which are generated all inside the superconductor, and these are called as vortices. Okay. So type 2 superconductors are those materials in which you create these these are all microscopic whirlpools which carry small magnetic field. There is a current circulating around them, and there is a normal core. It's no longer superconducting, but inside this there is normal electrons which are present. They cause some dissipation, they cause some resistance. So superconductivity gets weak, or it is lost inside these vortices. Okay, but these are localized, very small regions. Okay, and these are called as vortices. And these vortices actually arrange themselves into a well-ordered structure inside superconductor, and this was the prediction by Abrikosov, for which he in 2003 he got the Nobel Prize. So this was another Nobel Prize which went for the prediction about vortices. So if I apply a very weak magnetic field, then the superconductor is always in the Meissner state. Namely, it prevents all magnetic field from entering into it. But if I increase the magnetic field, then beyond a certain value, magnetic field starts penetrating into the superconductor, and it actually organizes, it forms these vortices, and these vortices actually organize themselves into a periodic structure. So the take home message is that there is two classes of superconductors, type 1 and type 2. Type 2 are the materials which have the maximum applications because you can use them up to very high magnetic fields. But the only thing is that in these materials, you have these vortices which are created. It is not like it's a homogeneous material which is fully superconducting. Beyond a certain field, you create these microscopic regions in which magnetic field penetrates into the superconductor through these vortices. Okay, these microscopic small whirlpools which are generated. But because of these vortices, what happens is that if you send a current through this superconductor, then these vortices experience a Lorentz force, which is I cross B, and because of that, these normal regions start moving and they start dissipating. They start producing dissipation. So in superconductors, we have seen that you want R is equal to 0 state. The resistance should be 0. But because of type 2 superconductors, where you have vortices generated, the R is equal to 0 state can be lost, because if you send in a current and you have vortices present, if these vortices move, then they will start these microscopic normal regions, these yellow regions which have normal regions, normal electrons, they will start moving and they will start producing dissipation. So therefore, although the other regions are superconducting, motion of these vortices will actually create dissipation. And it was this motion of these vortices which actually caused dissipation inside this material, because they carry very high currents. Okay, and they cause dissipation inside it, and therefore the material got hot. So because of the nucleation of vortices inside these and their motion actually generated dissipation and it created. This is actually a picture of a superconductor where these white spots, this is an image of vortex. Okay, this is an image of a vortex. There are a lot other images I could have shown you, but for now I'm just restricting it to just this image. Very nice images. If you go on the internet, you can look at vortices and superconductors where people have imaged at these length scales of few tens of nanometers. How does a vortex look inside a superconductor? Okay, and a current area from applications point of view is to see that what is the maximum current up to which you can actually prevent the vortices from moving, because if the vortices start moving, then you will have dissipation and it's no longer a resistance equal to zero state. Just because the vortices move, they generate resistance. So the lot of work is going on in trying to prevent these vortices from moving, and that's a very active area of research, so that you can apply these superconductors and maintain the R is equal to zero state up to higher values of current. Okay, so this is actually a movie which shows you how the vortices are actually entering into the superconductor. You can see the vortices actually enter inside the superconductor from the edge of the superconductor. Okay, and at some point the density increases so much that you will see a lot of vortices entering. Now, two more points, which is Cooper pairing. So, very briefly, the idea of how does the superconducting state emerge? Actually, when people measured this magnetic field or the flux inside the vortex, they found that this flux is actually related to the charge carriers in the superconductor. The amount of magnetic flux is related to the charges which are circulating around the superconductor. And using that, when they measured the amount of charge which was circulating in the superconducting state, they found it was not E, the electronic charge, but it was twice the electronic charge. Namely, the charge carriers inside the superconducting state are not E, but twice of E. And there were, of course, a lot of other experiments which were associated with that, but the basic idea is that inside a superconductor, the charge carriers are not E, but twice of E. That's the amazing thing, is that two electrons actually can pair up to actually give rise to superconductivity. And this was explained by Bardeen, Cooper, and Schrieffer, how this pairing mechanism comes about, because you know that electrons actually repel each other, but how is it possible that two electrons actually pair up to create this state? And a very brief and a very quick explanation I will just present to you here is that this is the lattice of atoms in which an electron is moving. So when an electron moves through this lattice, it will cause a temporary distortion of the charge ionic cloud around this. The positive charges will actually distort, trying to shield the negative charge which has been created. So because of this distortion, temporarily a positive charge is created, because this negative charge and these ions leave their neutral positions and they approach this negative charge. So this entire region gets positively charged. Another incoming electron sees this positive charge and gets attracted to this electron via this positive charge fluctuation. So this is how that the intermediate lattice distortion, momentary distortion of the intermediate lattice creates a positive charge fluctuation. It is momentary, remember. It is not a permanent distortion. The moment the electron comes in the vicinity of this, the charge neutralize, the ions start moving, trying to neutralize this negative charge and thereby giving rise to a positive charge fluctuation. And the next electron comes and gets attracted to this positive charge fluctuation. And that is how these two electrons get coupled via this intermediate positive charge fluctuation. And this is called as an electron phonon interaction. Okay, and that is how two electrons actually pair up. So these two electrons pair up, and this electron will be paired to the other electron, and in the process, you can create a complete paired state of electrons. This is an entirely paired state of electrons. the pairs are forming and breaking, but at any given point of time, every electron is paired to every other electron inside the system, and you get this pair. And you can think that it will be very difficult to push out a person from this pair, from this entire link, because this person is stuck to this person as well as this person. So it is not easy to push this person out or this person out, and so it becomes like a rigid entity. So this entire rigid entity can move through the lattice without scattering too much. If it was a single person, you can push that single person. But if it is like they are all getting coupled to each other, okay, through this intermediate fluctuation, then they are all tied to each other, and then it is very difficult to push a single person, because the other person will hold him and will not allow him to get pushed. So this was the explanation, and one of the major successes of superconductivity was the BCS theory. And in fact, this also led to a Nobel Prize. And if you recall, I told you about hydrogen sulfide becoming superconducting in the first few slides. It turns out to be a BCS type of a superconductor. So that is an amazing aspect, that BCS theory can also lead to such high temperatures of superconductivity, provided the ions which are making up the lattice are very low in their mass. And so hydrogen is very convenient to give rise to very small ionic mass, because if the ions are light, they can distort easily and they can create this fluctuation. So Bardeen, Cooper and Schrieffer have been a major success in the area of superconductivity. And however, the BCS theory cannot explain high temperature superconductivity or superconductivity in pnictides. So there is a lot more other theories which people are trying to develop. What is the mechanism of superconductivity which develops in high temperature superconductors? That has not been understood. And there are many open questions which still remain on the mechanism of pairing. How can you create pairing to actually create superconductivity? So this is another very active area of work on the pairing mechanisms. One pairing mechanism was the electron-phonon interaction. There are other pairing mechanisms which people speak of, but I mean the jury is still out, and it's not a final word as yet as to what is the best pairing mechanism. Finally, let me tell you very quickly about another important effect, which is the Josephson effect. That's another very important aspect of superconductivity. And if you recall from quantum mechanics course, that if you have a potential barrier, okay, and a particle which comes in if it's a classical particle, it will not be able to pass through this barrier, it will get reflected. But if it is a quantum mechanical particle, then the particle can actually tunnel through the barrier and go on the other side. So this is the wave function of the particle. You can see that the wave function is on this side. Once it enters the barrier, it's exponentially decaying, but it has a finite probability of the particle appearing on the other side, and with low amplitude, it will actually appear on the other side. So the particle can still tunnel through the barrier, okay? And this is another phenomena which actually occurs in superconductor. If you take two superconductors and you connect them with a weak interface, insulating barrier in between, then what happens is that Cooper pairs from one side can actually tunnel into the other side. So Cooper pairs from this side can tunnel into this, and Cooper pairs from this side can actually also tunnel into this side. So you can get currents which are circulating from here to here, from left to right, as well as right to left. Okay. And this is the phenomena of Josephson effect. It costs no energy. There is no dissipation. Tunneling will happen without any power dissipation. So you can have currents so you have these two superconductors which are actually separated by a non-superconducting region. But yet, if this region is thin enough, okay, if this region is thin enough, then Cooper pairs can actually tunnel from one superconductor to the other, and they can also tunnel back. And in the process, they give rise to Josephson currents, okay, which can actually go across this link. And so actually what happens is that the currents which are traveling from left to right and right to left, they actually interfere. there is an interference effect. Just like two light waves can interfere, similarly within this there is an interference of this light wave, of these currents actually, and this interference is actually controlled by the phase difference between the currents is actually controlled by the magnetic field that you apply inside this region. So just like geometrically, if you move in light, if you have two slits and if you separate the slits, then the path difference between the two light waves actually controls the interference pattern. Here in this interface, if you apply a magnetic field, then the magnetic field controls the phase difference between these currents which are actually circulating. Okay, and so there was Josephson relation, but this was the birth of another Nobel Prize, because Josephson effect is very important, and they use it in a device called a squid magnetometer, where there are these two Josephson junctions. This is one superconducting arm and this is another superconductor, and they are separated by this insulating region. Okay, and or these are called as weak links. Okay, and the currents which are flowing along this arm and these two arms, they actually interfere. So there is a device which is called as a superconducting quantum interference device. This is like a two-slit experiment where you have one light beam and another light beam which are coming from these two slits, and they interfere and produce an interference pattern. This is almost like that, but instead of a light beam, you are using currents. Okay, and the phase difference between these two light beams is controlled by the magnetic flux which is there inside this region. So the magnetic flux actually controls the interference between the light beams, and by looking at the interference of these two currents, you can actually measure the magnetic flux. So this method of measuring the magnetic flux by using interference of currents using the Josephson junction can allow you to measure very, very low magnetic fields. These are like 10 raised to minus 18 Teslas and even weaker. Okay, so under very special conditions, of course, you can reach this. But typically minus 6 microtesla, microteslas are very routine with this squid magnetometer, which is a superconducting quantum interference device. Interference is because of the interference of the current paths, and the phase difference between the interfering paths is controlled by the magnetic field. So this is a very important application device, and people use it in, they are developing for imaging the neural circuits in the brain. The magnetic fields which are generated by weak currents, they are trying to map those currents using these squid devices. In the stomach, you know, the processes which are going on, they are using these squids to actually look at the stomach processes and so on. So they have various applications. They are used as detectors of very weak magnetism in very small quantities. If you have very, very weak magnetism, you can use these squid devices. In quantum computations, there are these devices. You must have heard about this new area of quantum computation, which are actually using Josephson circuits, this Josephson device-based circuits for quantum computation. And the voltage standard, a Josephson is a circuit that generates stable voltages that depend on the applied frequency. So the definition of 1 volt is actually done by using a Josephson effect. So there is a Josephson circuit which is actually used where very stable voltage is generated depending on an applied frequency which is applied to the circuit, and you can define the 1 volt using that. So by applying a frequency, you can get a voltage, and then that unit of voltage is 1 volt, using which you can define the 1 volt standard. So just like you can have 1 kilogram length of 1 meter, the 1 volt is actually defined by using a Josephson circuit, a Josephson which is based on superconductivity. So there have been all these major new developments, and to finally end with the most recent developments, namely these are 2D materials which are called graphene. This is one single atom layer thick of carbon. Okay, this is just a monoatom layer of carbon which is called as graphene. Okay, this is a 2D layer of, it's a sheet of carbon atoms which is just one atom thick. Okay, And if you take these two sheets of carbon atoms and place them one on top of the other and create a mismatch of 1 degree, okay, this is the honeycomb lattice that you can see of these carbon atoms. If these two sheets are actually twisted by 1.1 degree, then superconductivity is found to emerge inside this bilayer of 2D sheet of materials. Okay, and the transition temperature is of course very low. The superconducting transition is 1.7 Kelvin. But this has given birth to a very new area of research where people are searching for superconductivity in these monolayer atom thick materials, and you can actually twist them, or you can actually misalign the layers one with respect to each other, and it will generate various sorts of other controllable property, where the property is controlled by changing the angle, the relative angle between the layers, and this has given rise to a new area of twistronics where superconductivity is also emerging. So this is a very new and modern area of research where again superconductivity is driving this field, where new things are being seen in this area. So with that, I sort of have covered most of the areas, the exciting areas, applications, topics. I have just given you a brief glimpse into it. If you pick up something and if you remember some of these words, Josephson effect, Meissner effect, vortices, 2D materials, twistronics, these are some things which are buzzwords which you will come across if you continue to study physics and look at this in the future. So with that sort of, I end my talk here. Thank you for listening, and Namaskar. Thank you.
Thank you, sir, for your wonderful presentation. So I think our students have learned a lot of things about the superconductivity, as it is very important thing. So we have got few questions in inbox and in comment section. So first
Okay.
we'll go in inbox. So what is the BCS theory? The first question, and what are the levitation features?
Okay.
Second.
So BCS theory is the Bardeen, Cooper and Schrieffer theory. So they tried to explain how does this phenomena of superconductivity emerge. So the idea is that if you have, let's say, a single electron, okay, if you take a normal material, if you have a single electron which passes through the atomic lattice, there are atoms which are present, there are these heavy atoms which are present, and you have a single electron which is passing, then this single electron will experience collisions when it is moving. So this gives rise to resistance. Now what BCS theory says is that the electron which is coming is paired to another electron, okay, and there is another electron to which it is paired. So you know there is an interpairing. So it is not like a single electron is moving, but it is like a train of electrons which are moving. It is like, you know, you have one person who is holding hands with another person who is holding hands with a third person. So it is like there is an entire train of electron which is moving, and if there is an entire train of electron moving, if you try to push one electron, or if you try to push one electron, the other electron will pull it back because of the coupling between all the electrons, because each electron is paired to another electron by the intermediate positive fluctuation which I had shown you, which is coming from the surrounding lattice. So all the electrons are paired with each other, and then it becomes very difficult to push an electron. A single electron can easily scatter, but if you have electrons which are holding each other, then if you try to push this electron, the other electron will pull it back, and therefore all the electrons get paired, and it gives rise to zero resistance. The scattering reduces and the resistance actually goes to zero. So this was the mechanism by which they explained the, I mean, very briefly, I mean, there are many aspects to it, but this is the feature, the main feature of BCS theory is that the conduction is not happening by a single electron, but it is a pair of electrons. There are two electrons which are paired by this intermediate positive fluctuation which is created, and it is this paired state of electron which gives rise to the superconducting phenomena. That is the basic crux of BCS theory. That's the basic central idea of BCS theory.
Okay, sir. Thank
What
you.
was the
So
other question?
what are the features of levitation? Levitation's features.
So yeah, so the features of levitation is that you can actually that when you bring one magnet close to the other superconductor, then this superconductor starts behaving again like a magnet. Okay, so if this is the north pole, then the other north pole is sitting here, and then these two north poles are repelling each other. So there is a repulsive interaction between the two magnet and the superconductor. So your material or the magnet starts floating on top of the superconductor. Okay, so that is the basic idea of levitation. With levitation, without any physical contact between the two objects, you can actually float one material on top of the other material, and there is no contact between the two. So that is the basic idea of levitation. But as I told you, that if you have two repulsive entities, then the equilibrium is an unstable equilibrium. So if you push it slightly, the system will fall off. So you need to balance it with attractive interaction. So that attraction comes because of vortices and pinning, but there are more other additional aspects to it. But the basic idea is that there are these two repelling entities because this superconductor is behaving like a perfect diamagnet. You can actually bring one magnet, and this superconductor now becomes like a magnet, and it also develops a north pole. So you have two north poles which are repelling each other, and one floats on top of the other. That's the basic idea.
So we have another question in comment section. So the first question in comments: so can cosmic neutrinos be detected with the superconductors, and how superconducting detectors can help us in neutrino mass measurement?
So for neutrino detection, that's an interesting question. I don't know exactly the answer. Maybe Pritham will have he is from the high energy area. Now, the thing is that neutrinos, as far as I understand, they have a very weak interaction with normal particles, with other materials. So because they have such a weak interaction with masses and other particles, it is, I feel it might be very, you might need to have a very large volume of the superconductor. You might need to take meters and meters of superconductor so that the neutrino can actually interact with the Cooper pairs and actually cause a breaking of the Cooper pairs and thereby give rise to detection of the neutrino. So perhaps it can be done, but what you need is a very large volume of the superconductor so that there is a little bit of interaction between the neutrino and the superconductor. It's a very interesting idea, but I don't know how feasible it could be because you might need to use very large volume of the superconductor for interaction.
Okay, sir. So there is another question. So what would be the Planck scale effect on superconductivity with the application of generalized uncertainty principle on it?
So, what do you mean by Planck scale? I didn't understand. Is it so? If you are talking of the size of the superconductor, I mean the Cooper pair is nowhere near the Planck length scale. The Cooper pair is actually much larger than the Planck length scale. It could be of the order of tens of nanometers. Okay, so we are not talking of that high energy scale. The Planck length scale comes at very, very high energy scales. The Cooper pairs, which are the fundamental particles, which are actually the charge carriers inside the superconductor, the quasi-particles, these are actually much larger in their size. Okay, and the typical energies which are associated with them are in the milli electron volts. Okay, so they are nowhere at the energy scales which are of the Planck length scales. If you want to reach Planck length scales, then the Cooper pairs will actually break. So much energy you will put that the Cooper pairs will actually break. So as far as I understand the question, it's not at that scale.
Okay, sir. So thank you. Thanks for your wonderful presentation and discussion, sir. So as the main aim of our program is to motivate our student in this corona pandemic situation. So I think some of our students have motivated as the superconductivity is very interesting topics of recent time. If we will find the superconductor in room temperature, then it will be more helpful for our technology. So thanks again, sir.
Absolutely. Thank
for
you. Thank you.
accepting our invitation, sir. And
It
hopefully,
was a
after the
pleasure.
COVID, we will definitely invite you for a face-to-face session, sir.
We hope to meet each
Bye for
other.
today, sir. Yeah,
Okay,
okay.
okay. Bye. Thank you so much. Thank
Bye, sir.
you.
Namaskar.
Namaskar. Namaskar.